Okay, so good morning everyone. I'm Pietro Zucca. I work in the astrophysics research group in Trinity College Dublin, and my supervisor is Professor Pietro. So what I'm trying to show today is one of the possible analysis of the height shock from a type 2 radio burst. And I'm starting with some an overview here. So first of all, I'm going to start to talk about what is a type 2 radio burst briefly, and how do we get from the dynamic spectra, the kinematics and the height of the shock. And then I'm going to talk about the key points that we need to analyze a type 2 radio burst, which are the density and the Alfvén speed. And I'm going to show how we produce two-dimensional maps of the density and the Alfvén speed. And then I'm going to just briefly start to talk about one specific study about the type 2 radio burst on the 22nd of September. So we all know what a type 2 radio burst is. This is from an observatory we set up in Ireland, the Ross Observatory. So it's a type 2 radio burst. We have fundamental and harmonic emission. And obviously we all know that the frequency is related to the density because it's a plasma emission. And also another characteristic of the shock is that the velocity of the driver, in this case for example CME, has to be faster than the Alfvén speed. And when this happens, then we have this type 2 emission that slowly drifts towards lower frequency as the density of the corona decreases with height. Now, what's the problem now is that in order to relate the height of the shock to the frequency, we need a density model. And the problem is this: I plotted here a couple of density models together with some data from some spacecraft, and we can see that there is a huge difference. We're talking about almost, order of magnitude, whatever model we can choose. So we need to tune this, we need to understand that. Another problem is all these models are radial models. And the type 2 radio burst can propagate in a non-radial direction. So we need to investigate how the density is. And in terms of the Alfvén speed, these are some of one of the models. This is from 2002. You can see that there is a local minimum at 1.5, 1.4 solar radii, and this is where most likely the type 2 emission is happening because of this minimum. There are also some 2D models. This is from Alexander, 2005, and you can see how the local minimum can be, depending on the position and the direction of the active region, magnetic field can be positioned in different locations in the solar corona. So we really need to investigate this in order to understand how the type 2 moves and how the shock moves in the corona. So what's important, what we have to investigate here is the density. And I'm going to propose here a density map from the surface of the sun, from 1 solar radii to 5 our sun. We created this using SDO-AAA and SOLASCO data. For the magnetic field, I'm going to use PFSS extrapolations and try to create a 2D map in order to get the Alfvén speed map. So let's start with the density. I'm going to use the emission measure from Alfvén 2011. It produces the initial measure using the 6 coronal filters in SDO-AIA, and it returns the emission measure for the solar corona. As you can see, the field of view obviously is limited to the SDO field of view, so at this point here we can arrive to 1.3 solar radii maximum, so it's limited to the field of view. So the emission measure is obviously an estimation also of the amount of plasma that is emitting in that line of sight. And if we know the line of sight, if we estimate what is the line of sight length in which the plasma is emitting, then we can get an estimation of the density. And there are a lot of studies made from stellar astronomers in the 30s and 40s, and they started to analyze the geometric path for the absorption of red stars, red giants, and they calculate how to get this length. So there are several examples in the literature, and we can estimate this. So here is the observer, and here this amount here of plasma is emitting, and we can calculate it against a density. For LASCO, we use a well-known method, which is the polarized brightness. So the intensity that we observe is due to the amount of electrons in the corona that scatter the light coming from the disk, and it comes here to the observer. There are several assumptions. The fact that the dust has to be discarded, has to be corrected. So the so-called decay corona. But it's a method. It's a well-known method. It's one of the estimations that we can get. So we can go from 2.5 to 5 arsan with this method. Now there is an obvious problem here. So we have SDO data 0 to 1.3, LASCO data 2.5 to 5 arsan. This is just an example of a radial profile in 1D. And we have a gap here, and we have to fill this gap in some way. And we're using models. So if we use just a normal spherical symmetric solution, this comes from the hydrostatic equilibrium, and using the ideal gas law, we derive this. This is the red fit here. I fit the LASCO data with this curve. As you can see, this is a single temperature. So we found that here, this is an active region, it's altered, and obviously it doesn't fit the quiet sun profile. For the active region, we used a simple plane parallel solution, which is just an exponential, and it's basically this equation here reduces to the plane parallel if r is smaller than 1 arsan. So if you're close to the surface, we can use the plane parallel one, which is the blue curve here. But obviously, dye is very fast to reproduce the quiet sun in the helper corona. Now, what we use in order to relate is the combined model. So a plane parallel plus a spherical symmetric, which is the orange curve here. And I've done this for all the radial profiles. And what happens here in a polar configuration is that this is the SDO data in density. So this is the position angle. 0 is the north pole, anti-clockwise to 360 degrees. These are all density profiles 1 to 5, almost 6. We're going to use only until 5 because then we don't trust a lot this border of data from LASCO. And the behavior is okay. So we have SDOAA, and we're going to replace with the model. Once I replace the model, this is what happens. And you can see we can reproduce with the model all these streamers, for example, they come out. So this is actually real data, and this in the middle is the model. It kind of follows the structure. At least it's better to use this data constrained model instead of just assuming a radial profile like a Newkirk or any other profile. This is a little bit more reliable, but at least it's constrained with actual observation of that specific day. So the corona is very variable. So in this case, we're using, when we observe the type 2 really bars, we produce that map to observe that day. This is just an example to how the density varies with position angle. We have corona holes in the order, of 1, 2, 3, 3 times to the 7 electrons as 1.1, so our sun, and it decreases fast here to just 10 to the 7 at 1.3. The behavior, it's as we expect. There is this double peak configuration. It's not here. It is in 2D. It's not very visible with the light here, but just to show a 2D map of density. Now, we need now to move to the magnetic field. For the magnetic field, this is just a 2D map. What we've done is use a potential field surface extrapolation, and its return is in a 3D configuration. We just extract the plane of the sky, and we can use. So these reproduces a lot of the strong features. There were active regions. This is for the 22nd of September. There were several active regions. You can see we can reach 500 and more Gauss. In the blue here, it's about half of a Gauss, and then it decreases. So using the density map calculated using the PFSS magnetic field, we have now an Alfvén speed map, a 2D Alfvén speed map, which is displayed here. We can see the speeds, the Alfvén speeds can vary a lot. We have the corona hole strong magnetic field, which returns a higher Alfvén speed. We have some local minimums on the side of the active regions, for example here, for example. And we have this sort of minimum structure as well on top of a strong magnetic loop. So the data that we have here, it's comparable with what we know from the models. So it's in a 2D configuration, which is important to have to study a type 2 radio burst. Now, I'm just going to briefly show one of the examples. These maps can be used to analyze all the type 2 radio burst on the lane, at least, because these are plane of sky maps. So I'm just going to show a little example here about the 22nd of September 2011. So there was an eruption, a CME eruption. These are 6 running difference from SDO-AIA. And as you can see, there is this feature which propagates which is eruption of the CME. Now, what we have done, we observed the type 2, the one I showed before, and I took one of the density maps, and I took several profiles, non-radial this time, because this is where was the direction of the propagating CME. So it says, where is the shock formed? So in order to try to understand that, I took this density profile. So for each of this density profile, I combined the SDO height time plot, this CME erupting, and I took with the height time running difference, I could take the height time of that. And also using the density relative to this profile, I extract a height time plot for the type 2. And this is what is get. Time versus height. The red points are the EUV feature, the CME. The blue dots are the type 2 radial burst height calculated using that specific non-radial density profile. And this is what happens. You can see in the lower region here, they don't match as but as we approach an upper portion, we can see that the kinematic is comparable, and then it returns to be a little bit. It doesn't match a lot of the radial profile, and it matches again in this other portion here. And so we have this kind of 2 areas where we have a matching height time plot. And also I plotted here 90 to 70 megahertz. It was the width of the harmonic backbone of the type 2 radio burst. So these are 2 density profiles computed for the harmonic plasma emission using this density map. So we think that the type 2 shock could have happened in this 2 regions when the matching height time matches the 2 density profiles. And so we don't have observation imaging for 90 megahertz. We have some radio universe data at 150, and here I just plotted on top of the 150 contour, and I see the emission there. Now I'm not saying this is the type 2 because it starts at I just find interesting that also the 150 emission matching these two positions. Now here, just to conclude, because I have a little bit of time, I also show how the Alfvén speed behave. This is the velocity versus distance, and this region here is the Alfvén speed calculated at plus or minus 20%, just to have an idea of the region. This is the SDO CME, and this is the velocity of the type 2. As you can see, it is super emphatic, at least it started to be super emphatic when the emission starts and it rapidly accelerates. This is for this radial, this profile, and this is for this other profile. Again, here you can see, because it's not a radial profile, the Alfvén speed does this double, it's not a monotonic function, so it increases in and again here I found that this is super emphatic, this is sort of emphatic. So I mean, this is just one of the examples of the use of these two maps. Just one message is that using a simple radial profile like a Newkirk or any other model, it's not really good to get the height of the type 2. With these 2D maps, you can start at least to understand maybe where the shock is coming in a 2D plane. And I finish then here with some conclusions. So we have the 2D density and Alfvén speed map. And I performed a sort of non-radial study, and maybe I think that it's an evidence of the shock to be formed in the upper flank region of this propagating, at least there is where the kinematic matches. So thank you for your attention.